All right, we're going to keep talking about rotational motion again. You know, what if we have a force applied to the merry-go-round? I've done this several times myself. We're going to be having a net torque acting on this. So this is a great example of torque equals I alpha. Okay, so our torque is going to be found by taking the force times our radius times sine theta, okay, or r cross f. So it's really probably better to take radius times force. In this case, we're perpendicular, so it's going to be times the sine, okay, of 90, which is going to be 1, and equals whatever moment of inertia this is. Now, this is an irregularly shaped object, but let's just pretend it's a disk. So we'll set that equal to 1/2 m times the radius squared, okay, times our alpha. And you can figure out your angular acceleration from that. Of course, you can bust out a rotational fat pi to find velocity, okay, when we're done. Okay, or, okay, remember you can do torque, okay, is delta L over delta T. Okay, so remember this. So if I take torque, multiplied it by the change in time that's happened, okay, I can set that equal to, okay, so moment of inertia in this case would remain constant, so I, and I can multiply this by omega 2 minus omega 1. I can do it that way also if I want a shortcut to figure out my final velocity. Otherwise, you get acceleration from that. Okay, and from that acceleration, you can bust out a fat pi to find final velocity. Now, what if a question later happens, okay, so that this band is no longer, you know, going around and around with this one, okay, and let's say suddenly a child jumps on this. I'll draw a quick child here. You guys know I can't draw it all, right? Okay, so we have a situation again where L1 equals L2, so he's no longer pushing on it. Okay, the beginning angular momentum is going to be I omega, so I'm going to have I1 omega 1 equals, that's supposed to be a W there, equals I2 omega 2. So I1, of course, is going to be 1/2 mr squared. Okay, and we'll multiply that by omega 1. So equals, now my I2 is going to be whatever mass that this person has and however far from the point of rotation this person is. So it's going to be an m, and I'll do like a big R squared for that one. Plus, again, the moment inertia of the rotating platform, which would be 1/2, okay, little m, little r squared, okay, and I'll multiply that by omega 2. Okay, so this is a conservation of momentum. So it was spinning initially, so 1/2 mr squared times omega 1 equals the sum of both moment of inertias. Now we have a point mass. This child's mass is completely going around something else, therefore that's mr squared, whatever, however far that person is from the point of rotation. And then multiplied by, again, the moment of inertia of our rotating platform, and then times omega 2. So that's a good review so far of our rotational stuff. Now, what about pulleys? Okay, let's just look at the pulley system here. Okay, once, you know, we have, now we're going to include mass in this situation. So how does this change? Well, let's say the pulley's at rest, not moving. Okay, we do have two torques involved when we're static, when we're not moving. Okay, we have, okay, an M2G this way, and then we have an M1G this way. So if I want the torque net on that very instant where this thing has not started accelerating yet, the torque net on that is going to be, well, let's assume that we're going to start to accelerate this way, would be M2GR minus M1GR. And the net torque is what's going to cause this to start to begin to accelerate. So this is static, though. It's not moving yet. Or I shouldn't say static. It's yeah, well, static. It's not moving yet. It's not at equilibrium, but it's not moving yet. Okay. All right, now let's take a look at the situation where we're indeed accelerating. I'm going to clear ink from the page here. So if this is accelerating again, let me draw this right here. This is the radius I'm talking about here. If we're accelerating, we do have a systems of equation. That's supposed to be letter R there. So straight down, we of course will have M2G here. And then upwards, we're going to have force tension 1. Okay, and then this way here, we're going to have M1G. And then upwards, we're going to have force tension 2. Okay, these two tensions are not equal to each other. Well, actually, since this one's called M2, why don't we make that one force tension 2, and we'll make this one force tension 1. Okay, now from the perspective of this, we have two different torques opposing. Okay, so from the perspective of this one here, we're going to have a torque this way due to force tension 2, and we'll have a torque this way because of force tension 1. Okay, now we're calling this direction positive now because we think it's going to accelerate this way. So I'm going to call the torque positive that way. I have to be consistent. Okay, so then I'm going to say force tension 2 times R. And again, we're perpendicular, so sine of 90 is still 1. Now we're going to go minus force tension, okay, 1 times R equals I alpha. Okay, and that's an alpha symbol there. Okay. Now, these equations, of course, this will be M2A equals M2G minus force tension 2. This one's going to be M1A equals force tension 1 minus M1G. And then we have three equations here. In this case, force tension 2 does not equal force tension 1. So, but we have an alpha in this, but we can substitute alpha, okay, does equal A divided by R. So we can substitute this in for alpha, or yeah, right here, and then we'll have everything in terms of A's and R's. And then you just solve the systems of equations. So that's how that is done. Okay, so that's the effect of when a pulley actually does have mass. And I showed you at the instant when it's not moving yet, you're two quick net torques, but when it's indeed accelerating up to that very, very small infinitesimal moment, we have to do a systems of equations. Video